Welcome. In this lesson, we're going to be learning about inverse relations and functions. We show an inverse function using the notation f of x and what looks like an exponent to the negative 1. But that's not an exponent. What this means, okay, so f of x, I want you to put this in your notes, with that negative 1 that looks like an exponent means inverse of the function. And specifically, this would be the inverse of some function f of x. If we had g of x with a negative 1 there, looking like an exponent, be the inverse of g of x. And so we have several ways to invert a function and find, in other words, find its inverse. So a function is inverted, and let's define that word. So inverted, that just means finding the inverse. Put that in your notes. So a function is inverted by interchanging the x and y values and then resolving for y. And this is solving for our inverse algebraically. We'll do this in a future lesson, actually the next lesson, but we will be doing that now. We also have another way, right? And I want you to add this all to your notes. Everything you see me right here, I want you to add to your notes. We could also just interchange the x and y. And we would use this method if we were given points or a table of values. And we will do this method in this particular lesson. The other way we can find the inverse of a function is to reflect it across the line x equals y or y equals x. It's the same line. And we call this finding our inverse graphically. In this lesson, we're going to learn a little bit about inverses, and we're going to find our inverses by interchanging x and y given a table or table of values or points, and graphically. So if two functions are inverses, then first of all, one undoes the other. So add this to your notes. So whatever the first one does, one undoes it. So one undoes the other, and vice versa. They undo one another. Secondly, inverses are reflections over the line y equals x. So that's very important about inverses. And third, everything about the two functions are opposite. X and y are switched. And not only that, domain and range are switched. There are some other features that are switched as well, but we'll see those as we get to different functions. Right? But this will be true for all of our inverses. Right? Everything about them is going to be opposites. Right? So if there's any other special features about a function and its inverse, they'll be opposite of one another. So on our graph there, we have two inverses. Right? So here we have two functions that are inverses of one another. So for instance, we won't talk too much about the functions individually, perhaps in another lesson, but let's just look at these points here. All right, so on the one graph, on the black graph there, the one that says y equals a to the x, this point here is the point 0, 1. On the red graph, the one that says x equals a to the y, that point there is 1, 0. Notice that x and y are switched. And notice that they are reflections over the line y equals x. How you can tell something is a reflection over the line y equals x, so this is the line y equals x, if you graph it and you connect the one point on the function and the corresponding point on the inverse, so this one's the function. So we'll call him f of x, and this one's the inverse, f of x, and then -1 there, that one would be the inverse. All right, so notice that segment connecting those corresponding points is perpendicular to our line of reflection here. And hopefully maybe you remember that from geometry. All right, so I'm going to write this on the graph, and you can write this on the graph too. All right, so segment connecting corresponding points is perpendicular to y equals x. So y equals x is always going to be our line of reflection. All right? So some features of functions that are inverses. We're going to learn a little bit more about features before we go and find them. So finding inverses graphically. Inverse functions are reflections across the line y equals x when graphed. We obtain points for the inverse by simply switching x and y in each solution point of the original function. Thus, we can say the domain of our inverse, right? So this just means inverse. The domain of the inverse will take on the same values as the range of the function. So f of x here is the function. Okay, so whatever the range is for your original function, that's your domain for your inverse. And whatever the domain is for your original function, that's the range for your inverse, because domain and range are switched. And since domain and range are switched, if we just switch x and y, we have our points for our inverse. So the graphs of relations and their inverses are related in an interesting way. And so not all of our inverses will be functions. We'll talk about when they're a function and when they're a relation. So you know, all functions are relations. They meet the definition for relations. And you learned about that, I believe, in Algebra 1. Right? For a relation, every x just has to be paired with any old y. Right? So all functions are relations. Not all relations are functions. Put this in your notes too so that you remember the difference. Right? So functions, each x is paired with one and only one y. So given x, I have to know which y to go to. Right? If I've got two different y's paired with one x, that's not a function, that would just be a relation. Right? So all the graphs of relations and their inverses are related in an interesting way. Note that we have points here on two relations that are inverses. Maybe they're function, I don't know, that's not enough to tell with one point. And notice that their x and y are switched. Right? So the graphs of ordered pairs A and B and BA always have symmetry about the line y equals x. Right? So notice that line segment there is perpendicular to y equals x, to that line. And that'll always be true. And you can use that to help you. And you can also use the fact that if you've got points, you can just switch the x and y. So we're going to find the inverses of the following functions. Right? 1, 3, 2, 4, and 3, 9. Right? So the inverse, and the -1 can go either here or on the other side. Right? I usually put it there. It's a nice little spot for it, but either way is fine. Right? So the points on the inverse, we would just switch. Right? So we have 3, 1, and let me make that a set. And we have 4, 2, and we have 9, 3. So all we have to do is take x and y and switch them. And that's it. Let's do the same thing here. All right, so our G is equal to, has 1, 3, 2, 6, and 3, 6. All right, so, and actually since there's just, it says G here, F and G are just another way to label the function. I can also just put the G with the negative there. I'll put the X there too, I guess. All right, and so to get the inverse, all you got to do is switch. So now I've got 3, 1, 6, 2, and 6, 3. And now my question to you is, are both the inverses, or are the inverses, functions? All right, let's see. And now I'll scroll down and show you the answer. All right, so let's see. I've got 3, 1, 4, 2, 9, 3. Right? We've got 3 different x's there. I've got 3, 1, 6, 2, 6, 3. Given on A, given 3, I know go to 1. Given 4, I know go to 2. Given 9, I know go to 3. On G, given 3, I know go to 1. Given 6, where do I go? 2 or 3? I'm not sure. All right, so are the functions, actually before I scroll this down, let me answer my question. Are the inverses functions? And on A was a yes, right? Because each x is paired with only one y value. Then I'll move it down. But B, oh, not so much. Right? B was a no. 6 is paired. Oops. My word paired doesn't look like a paired. 6 is paired with both 2 and 3, and that's no good. You can't be paired with 2 values and still be, an x can't be paired with 2 y values and still be a function. So can we predict in advance whether the inverse of a function will also be a function? And the answer is yes. Oops, move it down. Move down. We already know for a relation to be a function, no element in its domain can be associated with more than one element in its range. All right, so now if we look at A, the y values are 3, 4, and 9. That's our range. All right, so nobody repeats. If we look at the y values for G, we have 3, 6, and 6. If you see 2 of the same values, 2 of the same y values, or 2 of the same values in the range, then you know there's no way the inverse is going to be a function. Right? Because then when you flip it to make the inverse, you're going to have, the same x paired with more than one y. Right? So in addition, if the inverse of a function is to be a function, no element in the range can be associated with more than one element in the domain. That is, no 2 distinct ordered pairs in the function can have the same second component. In other words, the same y. A value that satisfies this additional restriction is called a one-to-one function. Right? And I think I've got that defined a little later on. If not, we're going to define it. I think I wrote down the definition for you. All right, because that's an important definition to know, one-to-one function. And its name kind of tells you what it means, right? One-to-one, 1x to 1y. Right? 1x to 1y. And I'll write that down next to my definition. All right, and here's I knew I had 1-to-1 on here. All right, so a function has an inverse, which is also, and you have this in your notes, a function has f as an inverse, f negative 1, which is also a function, if and only if f is a one-to-one function. Because the statement is an if and only if statement. It can be turned around without changing the meaning, right? If and only if means it goes both ways. Here we use the same statement as a definition for one-to-one, right? So we go one direction, we have a definition for whether or not an inverse is going to be a function. Go the other way, and you have a definition for one-to-one, right? So let's put a little star next to this, and we're going to, actually we'll put a star next to this one too, because they're both very important. So a function f is a one-to-one function if and only if no two distinct domain elements are paired with the same range element. Let's write down underneath that. We'll kind of clarify that. 1x to 1y, right? And 1y to 1x. That's kind of where its name comes from, 1 to 1. Every x is paired with one and only one y. And every y is paired with one and only one x. All right? All right, so put this part in your notes, the red writing in there, to help you remember what that means. It's easy to tell from the graph of a function whether that function is one-to-one. If any horizontal line can meet the graph of a function in at most one point, so if you draw a horizontal line and you never intersect the graph more than once, so I'm gonna underline this. Right, so horizontal, that is basically saying that a horizontal line intersects the graph only once. And I want to clarify that, add one more word to it. And that word I want to add is at the beginning. Just scroll everybody down there. And because maybe I can draw a horizontal line somewhere and it only crosses one point. I want any horizontal line. So if every single horizontal line I draw only intersects the graph one time, then it's going to be the inverse is going to be a function. If any horizontal line crosses the function in two or more points, the function is not to one-to-one and it does not have an inverse. All right, so write down what I wrote and then, oops, get rid of that. And now what I want to do is move it up and then underline the green and then underline this part as well. If any horizontal line crosses the function in two or more points, so we can get the end there without crossing out what I just wrote. The function is not one-to-one and it doesn't have an inverse. So underline that so you remember it. I'm going to try to scroll everybody up a little bit. I really don't want a box. I just want to scroll people up. And I got a box someplace else. So I'm just going to move my line up. There we go. And now my line is not over my writing. And you can read it. All right? So those are the requirements for our inverse to be a function and not just a relation. All right? It's very important to know whether your function, whether your inverse is going to be a relation or is it going to be a function, and why, and be able to explain why. So which of the graphs, so we have two, I put one on each page, otherwise it was too crowded. Which of the following graphs represents a one-to-one function? All right, so now if I draw a line, and because my line is probably not going to be straight, I'm going to use a line tool here. All right, and I guess I'll let it be black. Whoops, I must have hit the board. Now I've got this random line here. Whoops, I almost wanted to cut. Well, obviously I can't. So, there, cut. Cut. We'll get rid of all these little random lines. Cut. And now they're all gone, except for one. There we go. All right. So watch the line go. All right, here it goes. No, we're just moving the line, smartboard. Stop being a smart aleck. All right, so I'm gonna go over my writing there. Watch the line go. Do you see it intersecting 2 points? No, 1, 1, 1, 1, 1, 1. That's just 1 point here. That's 0.0. It's just flat. It's a little flattened out there as it's drawn. But look at that. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Everywhere, just 1 point. So because no horizontal line, because I dragged the same line to show you all the different lines, passes through any 2 points of the graph, f is 1 to 1. Here, we'll stick a line back on it. This one we have the line already drawn in here. I think you could look at it and see that's not 1 to 1. If I have a horizontal line, that's going to go through. That's going to go through my graph more than once. I'm hoping you didn't notice that I did not plug my computer in, and I'm on reserve battery power. I don't know if you see that too, but I'm plugged in now, so all is good. All right, so because a horizontal line can meet the graph of the function g at 2 points, g is not 1 to 1. Right? So over here on this graph, the inverse will be a function. On the other graph, oh, and add this to your notes. The inverse will be a relation, but not a function. All right, so now we talked about the requirement for our inverse to be a function, not a relation. It's easy to figure that out from points or a table of values. At least we can state it from the points we're given. And it's easy to figure it out from a graph. Right? It's a little harder to figure it out if you only have an equation, but we'll talk about that in the next lesson. All right, so reflective property of inverse functions. The graph of f contains the point AB if and only if the graph of f, the inverse there, I'm going to call it f inverse, okay? Because f negative 1, that's just weird. The inverse f inverse contains the point BA, and that's really what that means. All right, so we know that, in other words, x and y, I started to write the wrong y, x and y are switched between a function and its inverse. So here we want to find points for the inverse. Is the inverse a function? All right, so here's our inverse. Our inverse, we just switch to x and y. So it's going to be 11.8, negative 3, and 3.70, and 1, 1. Get the same point, huh? Switch 1, 1, you get 1, 1. And negative 12.56. All right, and let's check if this is a relation or an inverse. All right, so given 11.8, I go to negative 3. Given 3.7, I go to 0. Given 1, I go to 1. Given negative 12.5, I go to 6. Notice no x value appears more than once. So this is a function. All right, each x is paired with 1 and only one y. It doesn't matter that x and y are the same in the 1, 1, but each x is paired with only one y. Right? Nobody's paired with two y's. One and only one. Actually, make sure that's really clear. The phrase is usually one and only one y. Okay, so we want to graph the inverse of our relation here. Don't have a whole lot of great points, right? And so I don't want to figure out, estimate fractions, but I got a good point right there. That's the point 0, 2. Oops, sorry, that my comma looks so big, it looks like 0, 12. 0, 2. And this point, I know that point, although my dot didn't go to it. And that's the point 1, 2, 3, 4, 5, 3. And I know this point, and that's the point -5, 1. All right, so if the function has the points -5, let's go left to right, -5, 1, and 0, 2, and 5, 3, and solve this one along with me. Then the inverse, we just switch. That easy. And actually, if you remember graphing, this is just like actually, so actually before I write anything else, add this too. Graphing inverses is just like graphing, because geometry just did this, just like graphing reflections over the line y equals x. If you remember the notation, xy goes to yx. So they didn't know it, but they were graphing inverses all this time. You were graphing inverses when you were in geometry. So our inverse is going to be 1, -5, 2, 0, and 3, 5. Oops. I'm terrible at making that thing's called a brace. So this funky scribble here with some bumps, that's supposed to be a brace. For some reason I can't draw it very well. So, all right, so let's graph that. I'll graph it in red, make it stand out. All right, so here's the inverse. It's in red. All right, so 1, -5, right here, and 2, 0, right there, and then we have 3, 5. 1, 2, 3, 4, 5, right here. All right, and I need a line tool. Here we go. And then I'll make sure it's nice and straight. Actually, it's pretty darn good. Pretty darn good. I'll take that. That looks pretty good. And maybe just shy of the 1 point there. I think my dots is slightly off. This one right here. There we go. There we go. There is our inverse. Actually, I should have written in red to match the writing. All right, so here is the inverse. Now that's what's called a relation, but this inverse is a function. It's a linear function. So our inverse is a function. Because the original function is a 1-to-1 function. Linear functions are 1-to-1. Right, you're never you're never confused, right? One y value is not matched to two x values, right? It doesn't turn around, right? It's a straight line, right? Of course, every x is matched to one y. Very interestingly, let's find our slope here. All right, so the slope of the blue line is easy enough to find from these from the points that are written here. So the slope of the blue line here is 1/5. What do you think the slope of the black line is here? The one with the red points. Look at that. Our slope is 5. Here our slope is 5. Isn't that kind of interesting? And then I will try to graph it in a different color. Here's our line of reflection. I want a line tool, but I want it to be here. I'll just graph it in green. All right, so here's the line. It'll stand out because it's all dotted. All right, so here's the line y equals x in green there. All right, so that's the green line there. And notice that if I were to connect corresponding points, they would be perpendicular to that line. Right? So of course y equals 1, that has a slope of 1, right? Oops. Oh, that's a 1. It's kind of slanty there. Right, and let's find the slope of our the line that connects the corresponding points. All right, so there was 0, 2. Here's 2, 0. Those correspond because the x and y are switched. And notice that slope is 1. All right, so our y equals x is perpendicular to that line that connects (0, 2) and 2, 0, the corresponding points. I'll put 0, 2 and 2, 0. Right? So always true about inverses. I think I'm going to end this podcast right now. Stay with me for the next podcast, and we're just going to finish up, because we're almost done, graphing the inverses. And it's just as easy as switching x and y, or reflecting over the line y equals x, whichever you prefer. All right, bye for now.